20th century, in about 1900, in order to explain what is called black body radiation. Now, what is black body radiation? Well, the main point about it is it's thermal radiation. What that means is that it is what we call maximum entropy. Now, you see, I've talked about entropy and the second law of thermodynamics. And what does the second law of thermodynamics tell you? It tells you that entropy, in other words, randomness, is increasing with time. Now, what does this curve tell you? Well, you see, it tells you this is thermal equilibrium. And what is thermal equilibrium? That is maximum entropy. Now, there's a very profound mystery here, which, for some reason, cosmologists don't pay enough attention to. The mystery is a very obvious one, because we look at the earliest signals we get from the universe, they come from very close to the Big Bang. I should explain, it's not that close, because it's something like 300,000 years after the Big Bang. But that's a very, very small length of time compared with how long the universe has been in existence. So very, very close to the Big Bang, and what we see is this radiation, which has this kind of curve, and that radiation is seen to be maximum entropy. That's what thermal means. It's thermal radiation. It means maximum entropy. How did it start off as being a maximum, and yet it's supposed to be increasing all the time? And I think people got a bit confused by that, because they say, well, the universe is expanding, and so, well, it doesn't mean it's the maximum. But Tolman understood this very well, and he said, no, it's the maximum it can be, and the fact that the universe is expanding, the entropy is what they call adiabatic expansion. The entropy remains basically constant. So it was already at its maximum to start. So there is a huge paradox. It looks like a huge paradox, because it can't start at the biggest and then be going up ever since. Yes. Now, it's not a paradox for the reason which I want to explain here, because what we're seeing from this radiation, we're seeing radiation and matter which is at a maximum entropy state. So it's in most as random as it can be. Now, if it were really most random as it can be, that would be a paradox. But it's not, for an important reason. Now, let me tell you what that reason is. The reason is that we are looking at radiation. Let me cover up the bottom part for a moment. Suppose you have a gas in a box, and here we have the gas initially tucked up in the corner with compartment. You open the compartment up, the gas spreads out through the box. Now, this represents increase in entropy. So this is right. If it was tucked up in the corner, it would be a much lower entropy state. If it's uniform over the box, that's a high entropy state. So you have entropy increasing as time increases. That's supposed to be consistent with the second law, if that was a gas. Now, suppose that this was a lot of stars in an absolutely huge box, let's say a galactic scale box, and these were stars, not molecules. Then, because they gravitate, they attract each other, they would start to clump. And so, if you start off with a like random distribution and let them go, they will start to clump. So that if you have gravity in the picture, although entropy is still increasing in this direction, it's looking very much as though the uniform state is not the state of maximum entropy anymore. Because when gravity is present, it starts to clump. So we have something which looks like a combination of these two pictures, which looks like the gas. It's very uniform over the sky, but as far as gravity is concerned, it's a very special situation. And as time goes on, it will clump, and you get a very much of an increase in the entropy when you form these black holes. I'll come to black holes later on. They're very important in the discussion. For the moment, let me not talk about black holes, but just talking about the clumping which takes place. Suppose there was a uniform gas in the early universe, spread out, and then it starts to clump because of gravity. Now this is very important because we depend on it. And why do we depend on it? I have here a picture which is how life gets supported in our universe. You might say, well, why are we all alive? One of the most important reasons is we get energy from the sun. Here's the sun giving energy to the earth. But that's not a good reason. Why is it not a good reason? Because the earth does not get energy from the sun. In the daytime, it gets hot, but in nighttime, it cools off, and the heat goes back again. So if the heat kept on coming into the earth, it would get hotter and hotter and hotter and hotter. Well, it does to some degree because of global warming, but that's a much smaller effect than if radiation did not go away. It would be terrible. We would be all dead in about 3 days. So it's a good thing that the energy goes away again, because if the energy didn't go away again, we would just heat up and heat up and heat up, and it would be no use to us at all. The important thing, and this was a thing that was pointed out by Schrödinger in his little book, What is Life? Schrödinger made the important point that the energy that we get from the sun is hot, which means that it's basically yellow. Sky is basically infrared, it's cold. What this means is that the photons that come from the sun are individually much more energetic. The photons which go back out are individually much less energetic. This is the Max Planck formula coming in, who says that E equals h nu, the energy is proportional to the frequency. So if you have a high frequency light coming from the sun, that's the yellow light, and low frequency light going away, you need many, many, many more photons to carry away the same energy as comes in. This is many, many more degrees of freedom. The energy is spread out over many degrees of freedom. It's much more random. It's much more higher entropy. The point is, what we get from the sun is not energy, because the energy goes back again. We get energy in a form which is low in entropy. That is, it's in little parcels, a small number of degrees of freedom. The plants make use of this. They build up their substance, and we eat plants, or we might eat animals that eat plants. The point is that the plants take advantage of low entropy energy which the sun produces to build up their substance, and that is what we use to live on. And it's because of the low entropy in the sun, which is why we survive. And why is it low entropy? Well, the point is that the sun is there at all. It's quite complicated because of thermonuclear reactions and all sorts of things like that, but they're all secondary things. The main thing is that the sun is there. And the sun is there because it is clumped together by gravity. And the distribution of material was uniform previously, but because the material gravitated, and then it got hot, so the sun's a hot spot, dark sky. Dark is the imbalance between hot and dark is the neutral. If the sky was the same temperature as the sun all the way around, it would be completely useless. We would all be roasted, of course. It is also useless to any kind of creature. There would be no way of taking advantage of it. What we take advantage of is the difference in temperature between the sun and the sky, and that comes about because gravitational clumping. It's the sun was clumped gravitationally and got hot. Okay, there are other things taking place, thermonuclear reactions and so on, which are also important, but the main thing is that the sun is hot in the dark sky, and that is where the entropy is not at its maximum. So as time progressed, well, let me put it another way. There is this reservoir of low entropy in the uniformity of the universe. If the universe had already clumped and was very, very irregular, it would be no use to us. But fortunately, the universe started out very, very uniform. And this is a great puzzle. It's a puzzle which is not solved by inflation. And I want to try and say a little bit more about this. First of all, let me say a little bit more about the, I put one of the picture away that I didn't mean to, just a second, about the situation of the black hole. You see, this represents a very strong increase in entropy. We're not to that stage in our solar system yet, although our galaxy does have a black hole in the middle of it, which will be important for what I want to say, but as far as the solar system is concerned, we're not at this stage. So let me talk about black holes, because they will be important in what I want to say. Now, most of my pictures will be, in some form or another, space-time pictures. And space-time pictures require understanding what space-time looks like, and this means we have to understand the geometry of space-time, and the most important thing in the geometry of space-time are the light cones. So here we have a light cone, and what does this mean? Well, you see, at every point in space-time, you must imagine, in your imagination, there is drawn one of these little cones. This cone tells you, it's got a past cone and a future cone, this time is going this way still. It tells you what a flash of light would do, and this is the spatial picture here. So there is the flash of light in the middle. The next moment, we have to think of the light as, next moment we think of the light flash is moved to here, and that's this part. See, I don't have enough dimensions in my picture here. This is really a two-dimensional sphere as the flash of light comes out. This is really a two-dimensional sphere here as the flash of light comes out. This is the spatial picture, flash of light there, next moment, next moment. Flash of light, next moment, next moment. And this, you had an imploding flash of light, that would be the past cone. So you see, if there happened to be a flash of light here, the light would actually follow that cone. But you have to imagine that these cones are, in principle, there everywhere in space-time. It's just that if a flash of light took place, it would have to follow the cone. Now, the special theory of relativity is introduced by Einstein, and this is Minkowski's picture. Minkowski showed Einstein that his theory was really geometry. It's geometry of 4 dimensions, and it's the geometry of 4 dimensions where you have these cones always. And here we have light, flash of light, or photon, if you like, a little particle of light. It goes along, has a history at its world line, which is tangential to the cones all the time. As time progresses, the light goes along, and it always goes along the cone. That's what the cone is telling us. If it's a massive particle, it has to be slower than light, and so the world line of that massive particle is always within the cones. Now, in general relativity, these cones are not uniformly arranged. Gravitation influences the cones, and they bend one way or another. I have another picture here, which shows you everything going on at once, which is quite useful. Here we have light cones, and I have a black hole over here. See, here we get a flash of light. There's a massive particle, time going up, and at the overall side, we have a black hole. Now, a black hole is a place where the geometry gets somewhat distorted in a serious way. And I want to have my picture of a black hole, which is a picture where we have the light cones being distorted in this way. Here we have initially that time is again going up. Here we have some body, say a nova-massive star, which collapsed. As it collapsed down, it came within this region, which is called the horizon. Now, the horizon is a place where the cones, see, the cones get distorted. They tip inwards, like this, in both directions. They tip inwards, and there's a certain place, the outer surface of the cone becomes vertical in the picture. So this means that a signal cannot escape because, as you remember, the world lines of particles have got to be within the cones. So things can fall in, but they can't get out. This is the feature of the black hole. It traps anything which falls into it, cannot escape. So that is a picture of the black hole. Here we have an observer looking at it from a long distance, when you can see the light doesn't ever get into it, but it sees the surface down here. Let's not worry too much about that. The point I want to make, though, is that everything gets forced into the middle, and even with the irregularities present, you must get singularity in the middle. This is the place where the equations go wrong, physics goes wrong, we don't know what happens. It looks as though curvatures get so big that everything gets destroyed. And that is the picture we have. Not very nice, nevertheless, it's important for the physics that we understand today. Now, I want to try and modify the picture which I just had of the universe as a whole, and try to put some black holes in it. So here we have the universe as before, but I'm going to put some black holes in it. They will form, and they will get more and more as time goes on. Now, you see, if you fall into a black hole, not recommended, but if you fall into a black hole, let's imagine you were an eternal observer who started with the Big Bang and then fell into a black hole. That would be a singular boundary at the beginning and another singular boundary at the end. But they are very, very different in character. The difference is in the entropy. You see, the Big Bang was very uniform, and it was a very low entropy singularity. The black hole singularities are terrible things. They are very high entropy singularities. But nevertheless, you have to take them seriously. You believe that black holes are there. We believe that our galaxy has a black hole in its center, which is about 4 billion times the mass of our sun. So it's pretty big. There are other galaxies which have much bigger ones. The Andromeda galaxy has a black hole which is, I think, 40 times as big or something like that. Much bigger. There are even bigger ones than that, which we seem to see. So they seem to be out there. Now, since they seem to be there, what I want to try and say is, you could put inflation in here, it doesn't help. Why doesn't it help? There is something very mysterious about the beginning of the universe, which is that the entropy of the Big Bang was very low, which means it's very uniform. Now let me try and explain to you why nothing like inflation can help this. And I want you to imagine that the universe was collapsing. Now, I'm not saying that it will collapse. In fact, I don't think it ever will. But let's imagine it was collapsing. Certainly imagine it. And let's suppose that it's a little bit irregular. So this picture, if it's actually our universe turned upside down, it is very, very smooth in the beginning. But let's suppose there were small irregularities, very small ones, and they would build up, build up, build up. As the entropy increases, they become very, very irregular at the end. And the picture we would have is nothing like the one I have there. It's much more like this picture. That there were many, many black holes all congealing into one incredible mess. And that would be the fate of a general collapsing universe with the second law of thermodynamics, with entropy increasing and increasing and increasing to an enormous figure here. And that is something that we would expect in a theoretical collapsing universe. Now, since the equations allow that, and these equations can include not just Einstein's equations, they can include all the equations that you want to put in for inflation, fine, doesn't make any difference. The picture will be, I think I've actually chosen my picture. I think I had it mirrored, never mind. Here we have our universe, and there we have the like that. And we could easily have had a universe, theoretically, which was not like that, but like this initial great mass. It would be much, much, much more likely. Why much more likely? Because entropy is a measure of randomness, and